Assalamualaikum and hi doctor. In this video, we are presenting our assignment 3. In this assignment, we obtain the suitable dataset, which is supermarket sales for a prediction or classification model. Open the discussion, we have decided to use Python programming language to create our model. Part 1, model and dataset. The type of learning is supervised learning. Why we choose the supervised learning is our goal is to build a predictive model that helps us understand and focus supermarket sales based on various factors. We aim to identify key features influencing sale and provide insight to optimize marketing and inventory strategies. Description of the dataset. In this dataset, we have various features which is invoice ID, branch, city, customer type, gender, product line, unit price, quantity, tax 5%, date, time, payment, COGS, gross margin percentage, gross income and rating. The dataset consists of 1000 records and there are 17 input features including target variable. The problem statement is, in the retail sector, understanding and predicting total sale is crucial for optimizing business strategies and maximizing revenue. The problem at hand is to develop a predictive model that can accurately focus total sale based on various factors within a supermarket setting. We are choosing regression model because implements the regression analysis which could indicate the significant relationship between an independent variable and dependent variable to show impact of predictor on a target. Can be used to predict numeric value, used in forecasting, time series modeling, and finding crucial effect relationship between the variable. Part 2, machine learning algorithm. The name of algorithm we choose is linear regression. Linear regression is a statistical method used to model the relationship between a dependent variable and one or more independent variables. In the context of a presentation, you might want to convey the following key points about the linear regression. Linear regression is a statistical method that models the relationship between a dependent variable, which is total sales, and one or more independent variable, which is features. The linear regression model assumes a linear relationship between the dependent variable, the outcome you are trying to predict, and one or more independent variable, which is features or predictors. The equation for this linear regression is y equal to mx plus c. Why we choose linear regression? Because of the characteristic and strength. First, simplicity and interpretability. Second, effectively model linear relationship. Third, provide insight into the impact of each feature on the target variable. Alignment with objective. The goal is to understand how different features influence total sales, and linear regression is suitable for such interpretability. Next, I'm going to pass to the next presenter.
Assalamualaikum, my name is Najla binti Muhammad NIZAM. My matrix number is 294056. So next is clean data. So before we proceed with developing the model, we have to check if there is outliers exist between these two datas. So first, this is the code that we use to check if there is any outliers exist, and we use box plot. So the first one is unit price and it has no outlier, and the second one is tax 5% and it has outliers exist on the upper whiskers. And then before we clean the tax 5% data, it maximum value reach is 49.650000. Okay, so next, in order for us to clean the outliers, we use the interquartile range IQR method. And then we can check the total number of outliers removed. And as you can see, there is 9 total of outliers removed by using the IQR method. And then after we clean and remove all of the outliers, we can now see that tax 5% has the maximum value of 45.325000, and it is obviously different from maximum value reached just now. And then we check if there is any missing value for the data, unit price, and tax 5%. And there is no missing value for these two datas. And then this box plot shows that there is no outliers exist after we remove all of the outliers. Okay, so this is the code to train and test the data. So first, we use the linear regression as our machine learning algorithm. And then as you can see, the unit price is the list of the predictors, and the tax 5% is going to be our response variable. And then we split the data set into training and testing sets. So as you can see here, our test is 90%, which means the text size is 0.9, and then the random state is 0. And then we instantiate and train the linear regression model. And then we find the value of linear regression intercept and also the value of linear regression coefficients. So the value below, for the linear regression intercept, we got the value of negative 1.12756, and then the value of linear regression coefficient is 0.2911, which mean at one increase in unit price is associated with a tax increase of 0.2911%. And then we start to make prediction on the test set. And then we evaluate the model's performance using various metrics such as mean absolute error, mean square error, and also root mean square error. So for the value of mean absolute error, we got 7.03466. And then for the value of mean square error, we got the value of 81.2819. And then for the value of root mean square error is 9.0156. Okay, so for the next train test data is 80%, which means the test size is 0.8 and the random state is still 0. And then we instantiate and train the linear regression model, and then we find the value of the linear regression intercept and also the linear regression coefficient. So the value for the linear regression intercept is negative 1.28393, and then the value for the linear regression coefficient is 0.2929, which means at one increase in unit price is associated with a tax increase of 0.2929%. And then we start to make the prediction on the test set, and then we evaluate the model's performance, and the value of the mean absolute error is 7.0302. And then the value for the mean squared error is 81.4653. And then the value for the root mean squared error is 9.0258. Okay, so next string test data is 70%, which is the test size is 0.7 and the random state is 0. So we find the value of linear regression intercept and then the linear regression coefficient. So for the value of the linear regression intercept is negative 0.66433, and then the value for the linear regression coefficient is 0.2915, which means at one increase in unit price is associated with a tax increase of 0.2915%. And then we start to make prediction on the test, and then we got the value for the mean absolute error is 6.9563, and then the value for the mean square error is 79.90106, and then for the value of root mean square error is 8.9387. So for the next string test is 60%, which is the test size is 0.6 and then the random state is 0. So we find the value for the linear regression intercept, which is negative 0.4761, and then the value for the linear regression coefficient, which is 0.2829, which means at one increase in unit price is associated with a tax increase of 0.2829%. And then we start to make prediction on the test set, and then we evaluate the model's performance and get the value for the mean absolute error, which is 7.0039. And then the value for the mean square error is 81.3156. And then for the value for the root mean square error is 9.10175. So next string test is for 50%, and then the test size is 0.5, the random state is 0. And then we instantiate and train the linear regression model, and then we find the value for the linear regression intercept. So the value for the linear regression intercept is negative 0.15434, and then the value for the linear regression coefficient is 0.2748, which means at one increase in unit price is associated with a tax increase of 0.2748%. And then we start to make prediction on the test set, and then we evaluate the model's performance and get the value for the mean absolute error of 6.9928, and then the value for the mean squared error is 81.55074, and then the value for the root mean squared error is 9.03054. Okay, so for the next string test is for 40%, and then the test size is 0.4 and then the random state is 0. So we instantiate and train the linear regression model, and then we find the value for the linear regression intercept, which is negative 0.18288. And then the value for the linear regression coefficient is 0.2748, which means at one increase in unit price is associated with a tax increase of 0.2748%. And then we start to make prediction on the test set, and then we evaluate the models and we get the value for the mean absolute error is 7.00659, and then the value for the mean squared error is 81.2559, and then the value for the root mean squared error is 9.01421. Next, trend test data is 30%, which means the test size is going to be 0.3, and then the random state is 0. And then we find the value for the linear regression intercept, which is negative 0.1277, and then the value for the linear regression coefficient is 0.2741, which means at one increase in unit price is associated with a tax increase of 0.2741%. And then we start to make prediction on the test set, and then we evaluate the model's performance, and we get the value for the mean absolute error, which is 6.9855, and then the value for the mean squared error is 80.5678, and then the value for the root mean squared error is 8.9759. The next trend test is 20%, which is the test size is 0.2, and then the random state is 0. And then we find the value for the linear regression intercept, which is negative 0.1992. And then the value for the linear regression coefficient is 0.2787, which means at one increase in unit price is associated with a tax increase of 0.2787%. And then we start to make prediction on the test set, and then we evaluate the model's performance, and we get the value for the mean absolute error is 6.8568. And then the value for the mean squared error is 79.9491. And then the value for the root mean squared error is 8.9414. Okay, so for the last trend test data is 10%, which means the test size is going to be 0.1, and then the random state is 0. And then we instantiate and train the linear regression model, and then we find the value for the linear regression intercept, which is negative 0.2249, and then the value for the linear regression coefficient is 0.2787, which means at one increase in unit price is associated with a tax increase of 2787%. And then we start to make prediction on the test set, and then we evaluate the model and get the value for the mean absolute error, which is 7.2491, and the value for the mean squared error is 88.0017, and then the last value for the root mean squared error is 9.3809. Okay, so this is the overall result that we get, all of the values from the previous trend test data. And then as you can see, the best model is trend test 70%, which is the third fold, because it has the lowest value of the root mean squared error, which is 8.93874. And then fold 3, which is the 70%, is able to fit in the data set the best out of the 9 potentials models. So root mean squared error, RMSE, is selected as our main performance metric because RMSE provides an estimation of how well the model is able to predict the target value, which is the accuracy is high compared to the other metric performance. And then the lower the value of RMSE, the better the performance of the linear regression model in prediction, because it is closer to the actual values. And then RMSE is very easy to interpret and differentiate. So that's why we chose the RMSE.
Assalamualaikum. My name is NURUL binti BAHAZIR. My metric number is 295130. So I will explain about data evaluation. For data evaluation, we need evaluation classification model, which is accuracy, precision, recall, error rate, and F1 score. For accuracy is overall correctness of the model. Precision is the measure accuracy of positive prediction. Recall is the measure of the model's ability to identify all relevant instances. Is error rate. Error rate is the quantifies overall error in the prediction. F1 score is provide a balance between precision and recall. Next, we will compare the different fold ratios and identify the best performing. Based on the previous slide, my friend has explained about the mean absolute error, mean squared error, and root mean squared error. So based on the three error, we will find the accuracy, recall, precision, error rate, and F1 score. So this table shows that the value of the accuracy, precision, recall, error rate, and F1 measure for each ratio, which is 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, and 0.1. From this table, we can compare the values and can find the best value from the previous table. We can find the best model for each evaluation model, which is accuracy, precision, recall, error rate, and alpha measure. So for the accuracy, the best model is 0.7, which is 3078. Precision is 0.4, recall is 0.1, error rate is 0.5, and alpha measure is 0.7. Interpretation for accuracy is here the highest accuracy of 59%. It is indicating that it correctly classified 59% of the instances in the test set. For the precision, it is yielded in the highest precision of 59.6%. This means that out of all instances predicted as positive by the model, 56.6% were true positive cases. For recall, it is yielded the highest recall of 61.2%. This means that the model correctly identified 61.2% of all actual positive instances in the dataset. And for the error rate, it is yielded the lowest error rate at 49%. This means that the model trained and tested on equal proportion of the dataset achieved an error rate of 59%. And lastly, for the F1 measure, it is yielded the highest F1 measure of 59.4%. This is indicate that the model achieved a good balance between the precision and recall, considering both false positive and false negative. Next, let's take a look at the insights of performance of the model. For accuracy, the range from approximately is 38% to 59%. A higher accuracy indicates that the model predictions are closer to the actual values. For precision, the precision range from approximately 38.4% to 56%. A higher precision indicates that the model makes fewer false positive predictions, resulting in a higher proportion of true positive prediction among all positive prediction. For recall, the recall range from approximately 36 to 6% to 33 to 8%. A higher recall indicates that the model effectively identifies a higher proportion to all actual positive instances in the dataset, minimizing false negative. And for the error rate ranged from approximately 41% to 62%. A lower error rate indicates that the model makes fewer incorrect predictions, resulting in a higher overall prediction accuracy. And lastly, for the F1 measure, it is ranged from approximately 37.7% to 59.4%. A higher F1 score indicates that the model achieved a good balance between precision and recall, considering both false positive and false negative. Lastly, we will discuss about the limitation and challenges. The limitation and challenges is the data variability. The performance of the model may vary significantly based on the specific datasets used for training and testing. Next is hyperparameter tuning. The selection of hyperparameters such as the threshold for binary classification or the choice of algorithm can significantly affect model performance. Next is computational resources. Training and evaluating model using multiple split ratios and metric can be computational intensive, especially for a large dataset or complex model. And the last limitation or challenges is the generalization. Models trained on a specific dataset may not generalize well to unseen data from the same or different distribution.